giving you any new sheets today. We're going to go over the homework in a minute. But I just want to go back to related rates day 2. We had done the do now already. But I want to go and get to the shadow problem. After we just kind of review just related rates in general here. So how do you even know when you're reading a problem if it is a related rates problem? What are some of the clues? Yeah. Yeah, if you're given a rate and you're asked for a rate. You're given a derivative, bless you, and you're asked for a derivative. So that's the clue. They tell you the rate at which something changes is this, and they want to know the rate at which something else changes. So you're given a rate, which is a derivative, and you're asked for another rate. Or another rate. So you're given one rate and asked for another rate. That's how you know you have a related rates problem. So then you got to know what to do if you have a related rates problem. You say, okay, I know it's a related rates problem. What's the first thing you should do? Yes, Jan? Yeah, you want to draw a diagram. And what else do you want to do when you draw it? When you draw that diagram, you label. Yeah, you have to label any length that's changing with a variable and any length that's not changing with a number, with a constant, okay? So you want a diagram and label changing quantities with a variable or changing lengths. This always turn out to be lengths. Changing lengths with a variable and constant lengths with a number, a constant. And constant lengths with a constant. Nice. Now, if I had more room on that line, I'd also say figure out what derivative that you're looking for and which one they gave you. Oh well, no room. Okay, so you did all that. Now you move on to step 2. Now, and hopefully at this point you do know what derivative you're given, which one you're looking for. What do you need next? Yes? Yeah, you got to have an equation, a formula that relates the quantities. So you got to come up with a formula. And it might be an area formula, volume formula, Pythagorean theorem, or similar triangles. There has to be an equation that lets you see how the quantities are related. So after you have this formula or equation, what do you do next? Yes, yes. Okay, yeah, you definitely have to, and I would, see, that really should have been thrown in that first step. Figure out what derivative, identify the derivative given, and identify the derivative that they're asking you for. So I really should put that in my first step. I'll put that up in here. And identify given and asked for derivative. I'll just say given and asked for rate. Given, I can't put that in there, and asked for rate. You can put that in there. So you have to know, yeah, what derivative you're looking for and which one you have, because that's going to tell you what formula you need. So now you have a formula. What do you got to do? Ryan? Yeah, with respect to what? T, and T stands for time. Good. So you have to differentiate with respect to T. It's always d something dt. So differentiate WRT with respect to time. So now you're going to have an equation that has like the VDTs, the ADTs, whatever. It's going to have derivatives in it, and then what's left to do? Plug in everything they gave you and solve for the unknown derivative. So that's when I say plug in and solve for the unknown derivative. Plug in everything they gave you and solve for the unknown derivative. So you're just going to wind up with an answer where the units are ratio. Yes? Under 4? Step 3, differentiate WRT with respect to time. So everything is never with respect to x, always with respect to time. So let's say you go through all this, you solve for your unknown derivative, and you get a negative answer. Does that mean you made a mistake? Now, what does it mean? Yeah, whatever that is, it's decreasing. That quantity is decreasing. Good. So that's the idea of related rate problem. So we were up to the shadow problem and didn't do it, or? Okay. Let's do the shadow problem. Then we'll talk about the homework for the remaining time. I'll make sure we do a good job with the shadow problem. This is on rates day 2. Yeah, I know there was a rate, and I gave you one on Friday, but we didn't get to this one problem. I have to do the shadow problem. It's a classic. So you got this guy, 6 feet tall, walking at the rate of 5 feet per second toward a street light. That's 16 feet above the ground. At what rate is the length of his shadow changing when he's 10 feet from the base of the light? What should we do for a diagram? So you got to draw a street light that's 16 feet tall. You can make it as fancy as you want to. I know, mine's like pathetic, but it's a street light that's 16 feet tall. Kind of nice. Just a giant light bulb on a stick. 16. Okay. Now you got to draw your guy, 6-foot person walking toward that street light. Right there. Whoa, that's a long torso. Whoa. Wait, does he have an extra joint? I think he's got an extra joint.
He's like running to the light.
Yeah, no, he's happy. Gonna get to the light. Don't run to the light. Okay. We're good? Now, the question is asking about his shadow. What causes a shadow? Light being blocked, right, by his body. So I want to see where his shadow is going to be. So it's going to be when the light beam, oh, it's not bad. Here's a shadow over here. And this is a shadow. This is a darn good diagram. We have to make sure that we've labeled the lengths that aren't changing with numbers. Are there any lengths that will be changing that we need? Because we are going to be looking for the rate at what rate is the length of a shadow change, and we're also told he's walking at the rate of 5 feet per second. So what lengths are we going to have to worry about that are changing? Yes, right. Yeah, what do you want to call it? X, lovely. That's so lovely. We're going to let X be the distance between the guy and the lamppost. And the other lengths that are changing that are going to be important in this problem? Yes, Dan. The shadow. What do you want to call it? S for shadow. Okay. I'm warning you, kids. My S's look like 5s. I'm going to try real hard not to make them look like 5s. It's an S. That was good, right? All right. It's not going to stick. Yeah. I'll try. Okay, so now we've done all the labeling. Now we also have to figure out what derivative they gave us and what derivative they're asking for. Find the given derivative in the problem. 5 feet per second. That's definitely a derivative because you look at the units and the units like a ratio. So that's your given. Remember, with that given derivative, you have to decide if it's positive or negative. But it's d something dt. We got to figure out d what dt and is it positive or negative? D what dt? I don't even see a v in this problem. If he's walking at the rate of 5 feet towards the light, yeah, it's this length that's changing, right, at that rate. So it's dx dt. Right? If he's walking, this distance is changing at 5 Okay. Now, should I write down that keep it positive 5 feet per second or negative? Negative because x is decreasing. Nice. Good job. All right, that's the given derivative. Now let's look at the question. At what rate is the length of the shadow changing when he is 10 feet from the base of the light? What are they asking us for? The SDT. You've all noticed when you walk along, sometimes when you're walking toward or away from a light, the length of your shadow changes, right? Ever wonder? I wonder at what rate that's changing. So we're looking for DSDT when x equals 10. We've got dxdt, we want dsdt. Once you've done this, look at the variables in the numerators of your derivatives. X and s. That tells you that you're going to have to come up with an equation that relates x to s. So when you take the derivative, you'll have a dxdt and a dsdt. So look at what you've got here. I need an equation that has an x and an s in it. Let's see. Any ideas? It's not an area or a volume formula. That wouldn't make any sense. Yeah. Is it what? Pythagorean? Is that what you said? Similar triangles? What's going to give us, yeah? Because you have similar triangles? Yeah, the only reason we don't want to go Pythagorean theorem is because we don't know anything about the hypotenuse, nor do we want to. So that's not coming into play here. So I think that's a good idea. You see that these triangles are similar? So now we have to think, there are different ways to set it up. You just have to be consistent. So I don't want to, all right, Gina. Okay, so she's saying the big triangle, 16 is to 6 in the little one, taking the corresponding sides. So 16 is to 6, and this is the part that sometimes people mix up. What did you say for the numerator? X plus s would be the length of this whole side. You got to do the whole side of the big triangle, so that's x plus s over s would be the corresponding length of the smaller side. So she did 16 is to 6 as x plus s to s. Got our equation, but let's clean it up first before we differentiate. Sure. Did you have another way? I'll tell you if it's right. Mm-hmm. Perfect. Because as long as you're doing the same thing on one side as you are on the other. So you said 16, so you took biggest at big. 16 over x plus s is equal to 6 over s. That's great. Either way, when you're done, you're going to wind up with the same equation. So we'll cross multiply. Let's do it. 16s equals 6x plus s. Thank goodness someone remembered to distribute. Good? Cleaned up enough or no? Oh yeah, take away a 6s from both sides. So you have 10s equals 6x. That's nice. That is a nice equation. I mean, yeah, we could divide through by 2. But we don't have to. So we have 10s equals 6x. We subtracted 6s from both sides. Okay, so we've got that. 10x equals 6s. So you got your formula that relates the quantities in the numerator of your derivatives. So now we're all set to do what? Differentiate with respect to, so close, with respect to t. Okay. So what's the derivative of the left side? 10 minus 10 dx dt is equal to 6 ds dt. Good. And we have dx dt. So after you take the derivative, there's nothing left to do but plug in values. Yes? All right. I couldn't, thank you. Now you got to erase everything so I didn't copyright. 10s equals 6x, sorry. 10 ds dt equals 6 dx dt. And we know dx dt is equal to negative 5. Right? So this when x equals 10, it didn't even matter where you were. The rate at which the shadow length was changing had nothing to do with how far away you were. So once we put in the negative 5 here, you guys are going to be able to tell me what ds dt turns out to be. Negative 3? So ds dt equals negative 3 what? We always have different units. Feet per second. Nice. Does it make sense if he's walking toward the light that his shadow length would be shrinking? Because we got a negative answer. Yeah, right? So he's walking towards the light at 5 feet per second, and he's dragging along the shadow that's shrinking at the same time at 3 feet per second. Got that? Because here comes the second part of the question. They want to know, and just get the wording down, at what rate is the tip of his shadow moving? So they want to know how fast is the tip of his shadow moving. We know it's moving in, right? But, I mean, and we know how fast, we know the guy's moving, we know the shadow's shrinking, but we want to figure out how fast the tip of the shadow is moving. So I got to label a length where only this side is moving. I want the other side fixed. So we're going to have to call this whole distance here something else. What letter would you like? Y? Because if we want to know how fast the tip of his shadow is moving, we really want to know at what rate this distance is changing from the lamppost to the tip of the shadow. But you can't have the other end moving. You need this other end fixed. So in the second part, how fast is the tip of his shadow moving? What do we really need to know if we label that side Y? I'll call it B. Yeah, you want to know what dy dt is equal to. We know ds dt, we know dx dt, but we want to know dy dt. Since we know dx dt and ds dt, and we're looking for dy dt, if we could come up with an equation that has x, s, and y in it, that'll be fine. We can differentiate and get dy dt. What is the relationship between y, x, and s? What's the equation that links them together in this world? X plus s equals y. That's right. So now if we differentiate, what do we get? dy dt dt plus ds dt. So that's okay, because we know each of those. Dx dt was equal to negative 5, and ds dt turned out to be negative 3. So the rate at which the tip of the shadow is moving is negative 8. What would the units be? Feet per second. See if that makes sense to you. So you're walking along. If your shadow didn't shrink, okay, if it was staying the same size, the shadow tip would be moving the same rate you are, right? At 5 feet per second. But now, not only is the shadow tip moving because you're moving, but it's also shrinking at a rate of 3 feet per second, right? So the tip of the shadow, you see how it would be? You just have to add those two rates together. Because he's stuck to you and he's shrinking. So that shadow tip is moving at 8 feet per second. And it's negative because that distance is decreasing. Pretty neat, right? Thinking about the old shadow. Okay, let me just pause this.
I like how everything's in order.
Sorry, Sim's going through the potty. Okay, so here we go, guys. Let's go over whatever ones bug you. Let's go. They're gonna get better. We got to go through a bunch. Nope. All right, someone who's not saying every one, I'll hear from them. All right, Jan. Which one? 3. Perfect question to start with. Number 3. So in question 3, it says in the triangle above, and they show you have this right triangle. You have the angle, the hypotenuse is fixed at 5, and you got x over here. In the triangle shown above, if theta increases at a constant rate of 3 radians per minute, at what rate is x increasing in units per minute when x equals 3 units? Well, we have the diagram, it's labeled, but what derivative is given? Yeah, so 3 radians per minute. Well, that's somebody's derivative. Yeah, that's the rate at which theta is changing. Change in theta for change in time. And should we keep it positive or make it negative? Justify why you would make it negative. Okay. So it increases at that rate, so we're keeping it positive. At what rate is x increasing? What are they asking us for? dx dt. You did. That's great. And then it says when x equals 3. So when x equals 3, and they just said units. They didn't say centimeters or inches or anything. So that's it. Okay. So since you have d theta dt and you want dx dt, you need an equation that has a theta in it and an x in it. So what is an equation looking at this triangle? What of theta equals opposite over hypotenuse? Yeah, it's not cosatoa, it's SOHCAHTOA. Yeah. So the reason you would choose sine, you have a right triangle, it involves an angle. The reason you choose sine is for this angle, this leg is opposite, and that's the hypotenuse. So the trig function with opposite and hypotenuse is the sine. So sine theta equals x over 5. See why we chose that one? All right, you look at the numerators of your derivatives to know what your equation has to have in it. Okay, so now what's the time to do? Nope, not plugging yet. Yeah, differentiate first, then you can plug in values. Now we're taking the derivative with respect to time. What is the derivative of sine theta with respect to time? It's cosine theta d theta dt. Remember, theta is a variable, it's changing. Okay. Now on the other side, we have x over 5, otherwise known as 1/5 x, right? This is the same as 1/5 x, so what's the derivative of x over 5? 1/5 dx dt. So we got our equation, we differentiated with respect to time. Now it's time to plug each other, right? We're looking for dx dt, so that's going to stay dx dt for now. We know d theta dt, right? That's great. But this is where the kids go, oh no. We have to say what cosine theta is at this moment, and they only told me when x equals 3. How am I supposed to get cosine theta if all I know is that when x is 3? It is a Pythagorean trick. At that moment, when x is 3, do we know what this side is, the adjacent? 4. So at that moment, do we know what cosine theta is? What is it? 4/5, because it's SOHCAHTOA. Cosine is adjacent over hypotenuse. Yeah, sometimes they don't say when what you need is whatever. They say when something else is whatever, and you got to figure out what you need. You know, what is the value of that? Now we can solve this for dx dt. What would you do? You never can get that extended. Yeah, I'd multiply both sides by 5. That's an excellent idea, because that'll just knock that out. Multiplying. So much more fun than dividing. So dx dt equals 12. Now, as far as the units go, they gave us, you know, that x is, I think they even gave the units, it says in units per minute. They said at what rate in units per minute. Like they already, because x, they never told us exactly what it was. They just said units, and time is measured in minutes. So that's the dreaded trig one. You have a right triangle and theta's changing. You have to use SOHCAHTOA. Take the derivative and figure out what your new trig function is at that particular moment. All right, let's try another one. 4, I will tell you, is much more challenging than what I would give you on a test. 4 is the hardest one, so I think maybe we should skip it for now. Like, you can try to look through my solutions, but anything else is fair game. 9. All right, we're going to do 9. When the area in square units of an expanding circle, I'm just going to draw an expanding circle, okay. When the area in square units of an expanding circle is increasing twice as fast as its radius, then what is the radius that time? All right. So first of all, if you're talking, they're saying the rate at which the area is increasing is twice as fast as the rate at which the radius is increasing. Symbolically, how do we write down the rate at which the area is changing? Well, just like, you know, dA dt. So they're saying dA dt is twice as fast as the radius is increasing. So 2 times dr dt. So that's what they're saying. We have to translate it. And then, like, okay, solve for r. Well, we got to figure out what dA dt is, right? So I need to know the area of a circle so I know what to put in there. Or else I just have these 2 unknowns. I can't just solve it. So what is the area of a circle equal to? Pi r squared. So what does dA dt equal? 2 pi r dr dt. This is good. Because now, if, you know, right now we had, over there we had an equation with 2 unknowns we couldn't do anything with. But now, if we put in for dA dt, it's always equal for a circle 2 pi r times dr dt. We can solve this for r. See how we can solve that now for r? Before we couldn't. Because they just said that this is increasing. So dr dt is not 0. If it's changing, it's not 0. So I'm allowed to divide both sides by dr dt. And the 2. Oh, what's left on that? If I divide both sides by the 2 dr dt, we just have a 1 over here. So we have pi times the radius. Yeah. So at that moment, the radius would have to equal 1 over pi. Crazy. All right. That's another one I heard you guys saying, a couple of them. Yeah? Good one? They like your choices. When x equals 8, the rate at which the cube root of x is increasing is 1 over k times the rate at which x is increasing. What's the value of k? What? All right. First of all, when they talk about the rate at which the cube root of x is increasing, what does that really, how can I write that down? What do I have to find? The rate at which the rate at which anything is increasing is the derivative of it. So, well, what is the derivative of the cube root of x? Let's just take the derivative of that with respect to t. That's x to the 1/3. So the rate at which that is increasing is 1/3 x to the negative 2/3 dx dt. Okay, so right now we've got the rate which the cube root of x is increasing. So the rate at which anything is increasing or decreasing or changing is just the derivative. Okay, is, so I wrote down this so far because that's the rate at which the cube root of x is increasing. Then it says is, I'm going to write down for that. Mathematically, is equal 1 over k times the rate at which x is increasing. How do I write down the rate at which x is increasing? Dx dt. What is the value of k? Oh, when x is 8. So you see how we're translating these words? So the rate at which the cube root of x is increasing, so the derivative of the cube root of x, is equal to 1 over k times the rate at which x is increasing. That's just my dx dt. All right, so we got to find the value of k, and at the moment when x equals 8. Now we'll do a little plug and chug. Oh no, we don't know dx dt. Yeah. So it doesn't matter. You might be saying, oh no. Yeah, so since they cancel, if we put in 8, ooh, we're going to do that in our heads instead of going to the calculator. 8 to the negative 2/3 means 1 over, is it the square root of the cube root? Cube root of 8 squared. Okay. You do this power first? All right. So the denominator is 4. So we have 1/3. You could have taken the cube root of 8 and squared it. Either way. So you have 1/12 equals 1 over k. So, yeah. So 1 over 12 equals 1 over k. So k equals 12. That was very tough with the wording. The wording, yeah, right. But once you get it, yeah, the symbols is kind of the same. Why is our time going so fast? Because we're having fun. No. That's true. Did you get that number 8 right, the ladder problem? You didn't? You didn't? Oh, you got it. Okay. Yeah. So tomorrow we're just going to go over, yeah, I gave the review sheet and the answer key, right? But I want to go over what you, I'm going to try to pick like the most basic problems. Does this mean we don't have time to do any more? Number 6, what? Nice. This time, though, he's walking away from the street light. So now the given derivative, yeah. Are you making fun of my artwork? Oh, okay. I like it. Oh, thanks. All right, that was good. No chartreuse. All right, so I guess that's it then that's it. Oh, we didn't bring up the cone problem. Oh well, oh well.